All right, here we are on the next day of this assembly programming practice series, and I'm gonna dig into this problem that we took a look at the end of last time. Now, we sort of did some sketches of some ideas, and now we're gonna decide on which path to take and try implementing a solution. So let me start by recapping what this problem is and the ideas that I've looked at. So the problem is it asks for the first 10 digits of the sum of these numbers, where each line is a 50-digit number. So it wants us to treat these as just integers, in the standard way, and add them together. And then whatever number you get will be roughly 50 digits plus maybe two more, because since there's 100 numbers here, this could carry several times. So possibly as many as like 52, maybe 53 digits, and we're going to find the first 10, so the highest 10. Now, what's tricky about that is we can't just, for instance, add all the highest digit together and find out the first digit, because we don't know how much is getting carried over from previous digits. So this could have some carry, and how much carry it has might be influenced by how much carry this has, which might be influenced by how much carry this has, and so on. So there's not really a good shortcut, I don't think, for finding the high digits of a number. If it were low digits, it would be a different story. We could find the low digits without having to calculate the high digits. But to find the high 10 digits, I think we have to just calculate the whole thing. That's as good as I know how to do it. So what we're going to do is we're going to try to represent numbers this large sort of manually. So the issue is this is too big to go into a 64-bit integer, right? 64 bits can get you about 18 digits for any numbers and 19 digits for numbers that aren't too large in the 19-digit range. Like, if the first digit's a 1 and the second digit's no more than a 6, then you're roughly in the right range. But if you're looking at arbitrary 19-digit numbers, 64 bits isn't enough. So a 50-digit number is definitely not going to fit in a 64-bit integer type, right? So to recap what our ideas were, first of all, we were thinking like, okay, for one thing, how do you add two numbers together? And the more important part was like, how do you add big numbers together using small numbers? So it's like looking at the sort of long addition algorithm where you have like, okay, here we have three-digit numbers, and we're saying like this is for a human to do. So we have small numbers, as in each of them is a single digit, 197,315, and we have an algorithm that constructs the sum of all of that, like the big numbers, by only doing sums in the range that the human can actually do. So like you don't have to know 197 plus 315, or even have like some like clever tricks for working it out. You just run this algorithm, and the algorithm says like, well, take the first digits and add them together, and then put your low digit there and your carry up here, and then add those together, and then keep going, right? So that algorithm is a mechanical way that will give us a sum for a quote unquote big number given any two big numbers, as long as we already know how to add small numbers. So we took that and we interpreted it as we could represent big numbers in the range of 10 to the 50, 10 to the 52, 10 to the 53, whatever, using three 64-bit integers, because that gave us 192 bits, and 192 bits, we would only need 167 to get to 10 to the 50. We might need a few more to get to 190, or to get to 10 to the 53, if that really is how big it needs to get. But one way or another, 192 bits should be more than enough, because that gives us several million times more in range. So we were talking about building a 64-bit number, or a number that's three slots of 64 bits. And then the idea was, okay, first of all, we're going to create this new type. It's going to be called a U64 by 3. And we need to do three things in order to actually solve the problem. We need to be able to convert from decimal representation to a U64 by 3. So this is the decimal representation part, right? We just have a string of characters. We want to be able to convert that into U64 by 3. We also are going to need to be able to convert back so that we can find out those top 10 digits. It's we're not good. It's not good enough to just get it in binary. We need to know what it looks like in decimal. So we need to be able to go back the other way. And then we need the ability to add two of them together. Because then what we can do is take this and represent it as a big num, and take this and represent it as a big num, add them together, and we'll get another big num if we follow this pattern, 2 in, 1 of the same thing out. So that way we can like accumulate across this list, right? So we need to figure out how to implement these three things, right? That was the idea that we were exploring. Now, the add part isn't too hard. So we just sort of did the like, here's the long addition, but instead of using actual digits, we sort of broke it out. And you can see it's just like, you take the first slot, you add it together. You need to be able to ask what the carry is. So at first I was thinking of that as being arbitrarily large, but it turns out the carry, when you're doing addition, can never be more than 1 if you're adding two things together. So it kind of boiled down to this formula here, where we get, you know, a result slot 0 and a carry slot 0, and then we do a result slot 1, but it's like not the final one, and we have to take that and add in the carry 0, and that gives us the final result 1. And then the final carry 1 is the combination of the final carry value is the combination of the carries from these two adds. So basically after the first addition, we have two new digits or two new slots to add, plus we have to add in the carry. So it should be like A1 plus B1 plus the carry from slot 0. So that's 3 adds, which means 2 opportunities for a carry to occur. So we combine them, and then we add that in, you know, here we take A2, B2, and we add in the carry from 1. So that's the idea of how we would add them together. It's just that sequence of operations. The harder part that we didn't have a solution for right away was how are we going to do the conversions to decimal and back. And the reason that's hard is because the way you normally do those conversions is you have to be able to multiply and divide by 10. So like, for instance, you'd start by saying, look at this thing and do division by 10. And then when we do division, we get 2 results. One, we find out what this number is. You know, we get that number, and we also get that number, right? Division by 10 can be kind of seen as like chopping those off from this. So then if you're converting to decimal, then you take the number you've got, divide by 10, and that gives you a bit or a digit, and then you take the rest and divide it by 10, that gives you a digit, and so on. And once you've gotten to the point where you've done all of them, you'll get a 0 for the large part, like for the first part of the result of the division. The quotient part will be 0. And then you know you're done. You've converted to decimal. Similarly, to go from decimal to binary, you have to be able to multiply by 10, because you take one of these and you go, okay, well, how much is that 0 worth? Well, it's worth 0 times 10, but you know, then this one's just worth 0, but this one's worth 5 times 10, and this one's worth 2 times 100, and this one's worth 4 times 10,000. So you have to be able to keep multiplying by 10s or multiples of 10 in order to build up the actual binary representation from the decimal representation, right? Because when we see these, we have to say like, okay, we know that 5 showed up in a slot, but we want to add that in now. So the tricky part for doing these was that we were going to need to do multiplication and division of our big numbers by like 10 or multiples of 10. And those might, you know, we didn't have a plan for how that would look yet. So I thought of an alternative, and I'm going to explain now why I don't think we want to do this. So I'll make a note real quick of why we don't want to do this. So the alternative was that we thought, okay, looking at how this could get complicated here, maybe it doesn't make sense to use slots that are like binary numbers, right? 3 64-bit integers might be a mistake, because then we have to implement this. So the thought was maybe we want something that's a multiple of like a power of 10. So like, for instance, if you can imagine taking 18 digits at a time and saying, okay, those 18 digits, that represents 1 slot. So it wouldn't use the full range of what a 64-bit integer could be, but it would use a lot of the range. It would use more than half of the range of what a 64-bit integer could be. But it would not actually be the full range of 64-bit integers. Still, it would let's see, it would still fit in 3 slots, and it would make the conversions in and out much easier, because then you only have to be able to, you can basically say, all right, grab me the lowest 18-bit digits and then do conversion on that using multiplication by 10 and division by 10 in the 64-bit integer space rather than in the 64 by 3, right? Instead of doing 64 by 3s and multiplying by 10, you're just taking a U64 and multiplying by 10 or dividing by 10, and that's a lot easier because the CPU just has that built in, right? So then we don't ever have like a problem where we have to implement these and it's difficult. But the problem that it creates, and the reason I don't want to do it, is that it pessimizes addition quite a bit. So if we go back here and think about this, or I guess I'll make notes of it over here. Problem with this idea. Okay, so the problem with this idea is that would, let's see, pessimizes addition. And let's explore why exactly. So if I have 3 slots, I'll call them like A2, A1, A0, B2, B1, B0. I need to have A0 plus B0 here, low, and then the carry 0 here. How do we determine the carry? And this must be restricted to modulo 10 to the 18. So right, if this and this are 2 slots that we're adding together, and we're guaranteed they're both no bigger than 10 to the 18, that's great, but then this also has to follow that restriction. So that has to be no bigger than 10 to the 18. So how do you do it? Well, the way you do it is you add them together and you allow it to become bigger than 10 to the 18. And then you say, okay, use the division by 10 to the 18 to get the remainder and wrap this back into the allowable range. And if the thing we got back from the division is bigger than 10 to the 18, we'll get a 1 instead of a 0 as the quotient. And then we know that that's our carry. But that means the way we do all of this is we add divides into our addition algorithm. And I just don't like that. For one thing, divides are obviously a lot slower than adds and multiplies, and that means that if we're going to be building an addition operator for these U64s, and it was built entirely out of addition, that would be great. But if it's going to be built out of addition and division, then it's going to, it's going to be a lot slower to do those additions, right? And it seems to me like we're kind of optimizing for easiness rather than for the speed of the solution here. And it doesn't seem necessary because I don't think it's going to be simpler this way. I don't think it'll be simpler. I think it might actually be more complicated. I just think it would be easier because we wouldn't have to implement as many things to make this work correctly. But it would definitely be more complicated. We'd have to do these divides and manage the wrapping at 10 to the 18 ourselves. We're introducing an arbitrary modulus rather than using what you get naturally from 2 to the 64. And you're pessimizing your arithmetic operation so that if we were going to make this reusable in the future, we've kind of optimized it for the easiness of encoding and decoding to decimal. And if the problems get to the point where there's a lot more happening in the big number part where there's operations happening and not as many operations that involve converting in and out, if you can imagine, we convert in from decimal, we do some work, and then we convert back out to decimal. If that do some work part grows, we'll want the stuff we put in the, we'll want that part to be efficient. I imagine that harder problems will involve a lot more arithmetic between converting in and out, not less, right? So optimizing for easiness and optimizing for this conversion in and out doesn't seem like the right thing to do. And we can already do a lot of stuff to optimize the conversions in and out, even going down the original idea path. So I think it is wrong to pessimize this in this way. So we're going to try to figure out how we're going to do this. So an idea here is we don't actually have to do U64 by 3 times U64 by 3 or U64 by 3 divided by U64 by 3. We could just do a multiplier and a divider with U64. So let me explain what I mean in a little more detail. What if instead of So like right now, we don't have to go all the way. We don't have to do U64 by 3. Like we don't have to make our, let me make a little more space. We don't need a mul which does U64 by 3 and U64 by 3. To a U64 by 3, and we don't have to do a divide that does U64 by 3 and U64 by 3 to a pair of U64 by 3s either, right? So that would be the all the way version. We could do a simplified version. Where you take a U64 by 3 and you multiply it by a U64. And you get out a U64 by 3 still. So here we have a big number, here we have a big number, but here we just use a small number, right? And so that would actually be enough for us to do conversion in in from decimal, because we just need to be able to multiply by like 10, or in order to optimize it, maybe like 10 to the 18 or something in that range between 10 and 10 to 18. One of those 10 to the powers, one of those powers of 10 we probably want to be able to put into this slot, but we can get a pretty good power of 10 into that slot. Similarly, we could get away with, for now, implementing div small. And that would be something like this. So the quotient would still need to be a big number, because if you have something huge here and you have a 1 here, you gotta put the same thing here. But the remainder can't be bigger than whatever you put here. So we would be able to get away with a signature like this for small division, which would be take the big number and a small number and get the quotient and remainder from dividing those two. And again, we only need to be able to divide by things that fit in a U64 in order to do our decimal conversions. So I think that might be doable. So let's extend our plan. So we originally said our plan was to implement these three things, right? So we know how we're going to do this, and we could do this if only we had two other things. So what we'll do now is we'll say extended plan, or more details. So here are more details to the plan. We're updating it. So in order to implement this guy, we need mul small, which is a function like this, u64 by 3 times a u64. So those are the two inputs to our computation, and this is the output. And for this one, we need a div small. That would be a u64 by 3 and a u64, so that divided by that into a quotient and a remainder, right? So that's the updated plan. We want to implement this, these, and then we can use those to build these. So now all we need to do is come up with the details on how to actually implement each of these things. Okay. So let's look at long multiplication. The small variant. So what I mean by that is, what is it like? Let's look at like just the by hand algorithm first and learn from that. So let's say I needed to multiply 299 by 7, right? How do we do this? So we look and we go 7 times 9, that's 63. 7 times 9, that's 63 again, and we have a carry here. So that's 69. 7 times 2 is 14. We have a carry, so that's 20. Right? Then we scribble those out. So what we did there was like 7 times each digit, and then a carry part. I guess we didn't need to do the scribble part, right? So that's our result, 2093. So one big number, i.e. one with multiple digits, and one small number. i.e. one with a single digit. And the algorithm was not that big a deal, right? It was like multiply, and then we have a carry amount and leftover. Now let's take a look at how big a carry can get. In the case of base 10, the biggest carry is 9 times 9. So the biggest carry is always your base minus 1 squared. So in our case, the biggest carry, okay, I think I get what's going to happen. So the biggest possible carry is going to be base minus 1 squared. In the case of what we're implementing, that's going to be 2 to the 64. That's, if you think about it, we have 3 slots of U64s. So 2 to the 64 is the base we are using for our number system, minus 1 squared. And that's going to be a little bit less than 2 to the 128, right? Because you can imagine if this was 2 to the 64 and we squared it, we would just get 2 to the 128. And we're squaring something just one less than that. So it's like clearly less than 2 to the 128. I could, whoops, I don't want that. Can you go away? I can spell this out, I think, in a slightly more clear way. So this is strictly less than 2 to the 64 squared, which equals 2 to the 128, right? Maybe that clears up the idea. So, the carry always fits in a small number. That's interesting, right? So you don't need to deal with the possibility of carries that spill over when you're doing multiplication of two things at a time. The other thing is what happens when we look at but what if we add in a previous carry as well? So let me think. If we have our base number minus 1 squared, that's the largest thing we can get. We can take the base number minus 1 and multiply it to itself, and then add in the largest possible carry. The largest possible carry, well, we know it's not more than base minus 1, right? We just kind of worked that out. It's not more than base minus 1. I think it might be less than that because, like, I mean, in the case of base 2, it would exactly equal base minus 1. And I think the larger your base is, the more you lose from that inequality, right? This inequality becomes more and more pronounced as your base gets bigger. So here we're losing a lot by that minus 1 before we square. But we could just say, like, okay, so the largest it could ever be, which we are confident of, is base minus 1. Does that, can we prove that that's less than or equal to the base number squared? So this we could understand this as base minus 1 plus 1. Let me do this in several steps. Base minus 1 plus base minus 1. And that, now we can factor out a base minus 1. And what we have left over is a base minus 1 plus 1, right? So here, I'm taking this base minus 1 and this base minus 1, and I'm factoring them into here. And then this one goes here, and this has a little multiplier of 1. Maybe I could do this a little bit more cleanly. So this here and this here get factored out together into this thing. And there's a little imaginary 1 here. And a base minus 1 here, which get factored into that. Then this simplifies to base minus 1 times base, which is still less than the base squared. Yeah, so even if you add in the carry, your carry doesn't get too big to fit. So that's good stuff to know. Martin Loff has an off-topic question. I'll answer it real quick because it's interesting. It seems a lot of good programmers agree that having a real ISA for graphics cards would be great. What's your sense of why hardware companies aren't interested enough to do it? I don't really know. Like, I haven't spent any time understanding how hardware companies operate or like what kinds of forces drive the decision making. So I don't know. I could only repeat things I've heard other people say. I have no real opinion of my own about where that comes from. I do agree with the idea that like graphics programming would probably be better if we had an ISA for it. And I think like if I were to talk about just the technical stuff that I do understand, I think that it's fairly clear that if you take the system we have now and you toss it out and you build a new one based on an ISA, you will have a short-term dip in your ability to compete on like technical specs, benchmarks, stuff like that. The reasons for that are a little unclear to me, but it's pretty obvious in the sense that switching horses always has that effect. Like that's just the way things are. You're currently able to game the system, I guess you could say, in certain ways, and you'd have to throw out that playbook and learn a new way to game the system. And even if that isn't entirely artificial, like even if it's not totally bullcrap and it's like, no, you actually are literally for useful purposes slower, which I think would be the case, I think in the long run, it's where we would want to be. It would mean that everything could be done more simply, which means you could iterate more, which means you could get better. Like a lot of the times, trying to grasp too hard and too tightly on one aspect of the problem in order to make it perfect has the cost that you can't do a very good job on a bunch of other parts of the problem, and that your total result will actually turn out better if you give up a little bit on the thing you're trying to do perfectly and allow other things some room to breathe in the problem space as well. So it's all like totally theoretical, hypothetical talk I was just giving you there. To answer the last part of your question, do you know what other folks at RAD think about this? I don't exactly know what other people's attitudes are about it either. I think that it's probably the case that they agree that it'd be more simple and more convenient to program that way. I think the real where the debate comes down to is how the debate breaks out is like, would you recommend pushing for it now, knowing that there's probably a cost in performance in the short run? Is that a reasonable way to expect it to happen? So is it worth it to push for it from a political perspective? Is it worth it to push it for it from a technical perspective? Or are there other paths to get there? Like, I don't know. I don't know anyone's ideas of what that is like. But, my take on it is graphics programming is very complicated the way we currently do it. And that is so that we can get like some percentage more performance out of the hardware, and that means that while yes you're doing better in one dimension, you're also making your life so much harder along that iteration axis. You're making your life so much harder along that iteration axis that you don't really know what good things aren't getting done that like would make up for that loss of performance until you try, right? Okay, let's get back on the topic. So what we figured out is that for multiplies, the biggest possible carry is always going to be a small number. even when we add in a carry and then do a multiply. So if we had 9 times 9 plus 9, the carry would still just be a 9 in that case. Yeah, so it looks like, and this looks like, that seems right. So that means that what we have to do, now what we want to do is look at, okay, what is an abstracted version of this thing here? Okay, so suppose I have like A, which is in 3 parts, A2, A1, A0, and B, which is in 1 part, and I want to multiply them together. Then the abstracted version, we have A0 times, I'm going to write this in the A0B, the low part, and up here we have A0B, the high part. That's also could be called carry 0. And then what we have is A1B plus carry 0, the low part, and A1B plus carry 0, the high part, which is C1. And then here we have A2B plus C1, the low part. And finally we would have A2B plus C1, the high part. Okay. So we would again end up with 4 digits. This one could be any, I think, at least as far as we could tell, it could be any value from the base. And let's see, what else do we know? Yeah, so all of these carries can be any of the numbers from the base, not just one, like in the addition case. But besides that, what else? So since they can be more than just one, we aren't just going to be looking at a carry bit. We want to look at... Okay, yeah, so we have to figure out how we break apart, multiply, and add. So when we do a multiply, I think we do have a way of doing a multiply that gives us the low bits and the high bits. And what that means is we should be able to, like, let's start by just figuring out how we will get this. Let's look at that part. So, for instance, we've been using imul. If I use imul, do I get what I need? I don't think so, because imul has a destination register, so probably we lose the high bits. One operand form. Here, the source operand is multiplied by the value in the AL. Okay. Let's look at the mul instruction. I think imul is the one that does like normal, like C-style multiplication, but the full multiplier is just mul. Okay. Mul, here we go. An unsigned multiplication of the first operand, destination operand, and the second operand, source operand. Stores the result in the destination. This destination operand is an implied operand located in register AL. Okay, so yeah, this one does RAX times source and puts it into RDX RAX. So here we get the high bits. So we can do this, but we have to use mul, and we have to make RAX one of them. Like we can put make B. We can make either one of these RAX, make the other one B, and then we can multiply them. RAX and RDX then contain this and this. Now the next one gets even harder because we have to do that and then add that in, and the add might have a carry, which means we have to add one to the high part of this. So let's write that out as some code. Figure out what what series of computations. Here's an abstracted version. And now here we want to do what's the computation version? Okay, so for computation version, we want something like R0, C0. I'll use this notation. So if these are the high bits, these are the low bits, equal A1B. C1 hat, C1 bar, I mean R1 equals A2B. A1, A0, A1, C2 bar, R2 equals, and I think we're going to throw away the overflow in this implementation at least, A2B. These need to be bars as well. Okay, so that gives us the multiplies. But then we want to do the final R1. I see. So the C1 hat, that's the carry of the add part, and the R1 final value. So R0 final value, we already got it. R1 final value is the R1 bar plus the C0 carry. So here we get a 1-bit carry from the add. Then for R2, we want R2 to equal this guy here plus this guy here plus this guy here. And since we don't care about the carry, we don't need to do anything to separate these adds out. It's just add those three things together. This is a 1 or a 0. This is any 64-bit integer. This is any 64-bit integer. We add them together, we throw away the overflow, and we get our final value for R2. So that should give us a multiplier that does the small multiply. Again, this is not too complicated. What are we looking at? 3 add, 3 mul, 3 add. And we have to make sure that these muls here are happening with use the mul operator or instruction. That way we can get the high bits. I guess technically we can get the high bits with imul, but we don't. We're going to go with unsigned multiplication for this one so that we don't get any surprises. Okay, so that's how we're going to do multiply. One last one to think through is how are we going to do long division? I expect this to be the hardest one to figure out. But let's see. Long division. Small. Okay. So how about we start with the same thing we did with multiplication? So we're going to have like a long division sign here. I guess that's a pretty big one. Let's go like that. We're going to divide 546 by 3 using the long division method. Okay. So how many times does 3 go into 5? Answer 1. And then we have 3 times 1 goes here. We subtract those and we get a 2. Then we make a new number, 24. And we have to ask how many times. We know that this is this here is too small by itself. But we then combine that with this, and we should be able to do the divide onto this. So how about that? 8, right? So then we get a 0. Oops, not make that a 0. 6, and so 2 more. And finally, subtracting out the 6, we get the remainder of 0. Okay, so that's long division by hand using a small number. Now that's going to have some tricky aspects, right? For one thing, this part here, we had to do division by a big number. Like, anyway, it wasn't entirely here. So one thing we could say is here we did division of 2 small numbers. We did 3 divided by 5. Right, so that gave us division of 2 small numbers, which we can do. And then we had to do a multiply, so 1 times 3, and that gave us 3, and then a subtract, 5 minus 3. And that gave us 2. Okay, but then we had to combine that. So then we combined So that's where it gets a little weird, because once again you end up needing to do division by something big, or like it didn't break down all the way to small division, right? Like I can't solve 24 divided by 3 if I only know how to do division by single digits, and the long division method doesn't really tell you what to do in that case. I guess there is, okay, maybe I see what we need to do. Let's go look at the divide. Yeah, so actually, this whole time we've been using divide, we have to clear d to 0 and set a to the thing we want to divide, because we were treating it as just dividing 64-bit. So actually, when you use 64-bit mode, the numerator is treated as 128 bits by combining those 2 registers. So what that means is the way the divide is set up is that whatever your Oh, is there an unsigned divide? Yeah, here we go. Okay. Yep, that's what we need. So the input comes into from these two registers together. That way, you can do this case, right? 24 is just RDX has the 2 and RAX has the 4. And then the CPU is built with the ability to do a divide of 2 slots by 1. That way, and if we're doing division by 1 slot, we know that it's always going to be able to divide something with 2 slots by at least 1. So it will shrink this. So I think that we can do this. I need to take a quick break, run to the bathroom, and then we'll continue from here. Let me leave you guys with some. This is, I was playing at the beginning before I started recording, but I've got new music that is not a part of the that I've just recently created that has not been debuted yet, except in the pre-stream. Here you go. All right, I'll be back in a few. Okay. Let's get back to it. there any way to make wish I couldn't make it full screen, but anyway. So I think we're kind of closing in. If I remember where we were just at, I remember what line we were just on here. We're kind of closing in. We're kind of closing in on an answer. So yeah, let's look at the abstracted version of this. I'm switching from A and B to N and D for numerator and divisor. It's just a standard naming scheme I use for division operations in general. Since they have asymmetric roles, unlike in multiplication and addition. Okay, so what goes up here is N2 over D rounded down, and that's then we have D times N2 over D rounded down. What's a good name for that object there? Why don't we call that, this thing here, Q2. Q2, and then D times Q2 goes here, subtract. So at the bottom here we get N2 minus DQ2. And then we combine that with N1, we get a new number here. So Q1 becomes, and these are combined as like digit combination, Q1 becomes, round down, N2 minus DQ1 minus DQ2 over D. Oh wait, one. It's a lot to write. Q1. So then you subtract D times Q1. I guess we could give this thing a name. That would help. So that will be, and I'll just use C again, C2. So this becomes, well, let's call that C. I'll call it, actually what I'll do is I'll call this N1 hat, right? So then we have N1 hat is the thing that actually goes in here. And we subtract from n1 hat d times q1, and what you get left over is, and we have n0 here, what you get left over is n1 hat minus dq1 is one slot, n0 is the other slot. I think it like combined as slots like this. I don't know how to notate that, but it's something like this. Q0 is n0 hat over d, rounded down. Then we subtract d times q0. What we get left is remainder, which is n0 hat minus dq0. And we can transport that up here. Remainder equals n0 hat minus dq0. n0 hat minus dq0. Okay. So that's how the algorithm works when you just look at it in terms of what the symbols, how the symbols connect to each other. So it's a little bit more complicated than the other ones. We do this divide here, one slot by one slot, and then we take the result of that divide and isn't this just calculating a remainder? Couldn't we actually think of this as remainder? N2 times, I think that's right. So N2 divided by D, there's some like number of times it divides and then some remainder amount. If we subtract out this, what we're leaving is whatever the remainder is. So that makes sense, because on the last one, that's our final remainder. That's the actual total remainder. So the way these here are remainders, which means we don't have to do any multiplies to get them. Or subtracts. We could just use the remainder. In fact, this is all going to be just division. Strangely enough, in order to divide these big numbers, we're just going to use the divide operation repeatedly, which is kind of cool. In fact, our divisor is the same all the way through. So we can make RAX and RDX the numerator part over and over again and have the divisor just sit there. Yeah, that's actually that's going to be kind of a tight little piece of code. It's going to be neat. Okay, let's figure out what the computation of that looks like. Here's the computation version. So we need, what did we say? So we compute these in the other order. So I will call this, I'm not going to use the name n hat or c. I'm going to use the name r now because I realize that it's remainder. So r2 q2 equals, or rather, I'm going to write these with it in a different way. Q2 R2 equals N2 div D. So here we have the remainder from that and the quotient from that, right? And then Q2 is our actual result. R2 is our remainder. Q1, R1, is R2 combined with N1. So the remainder from that goes into the high part, and the the next slot down, the low part, div D. Quotient 0, remainder 0. Yeah, this is actually a simpler computation than the others, because maybe the divide operation, the divide instruction might just be perfectly like suited for long division. I don't know. R2, R1 and 0, div D. And then finally, our remainder equals R0. That's all there is to it. It's just 3 divides. That's like really, really cool. Okay, let's start trying to implement these things. So we want to, let's start by just trying to implement all the arithmetic stuff and test that out. And if that's working, then we'll go and implement the decimal converters and solve the problem, okay? So let's start with sum. Where was our plan for sum? Here, I'm gonna mark this up. So here I have abstract version. There's an abstract version of addition. Here's a computation version. Okay. So let's write these. Ooh, this is, I find this problem very exciting. We're getting to use aspects of the CPU that have always been there that usually you don't get to use. Like C doesn't actually make it very easy to, for instance, pull out the remainder from one divide and stick it into the high bits of a 128-bit slot of the next divide. But it's going to actually not be that hard. Oops, I'm sorry if that was loud. I'm going to put this over here so that doesn't happen again. It's going to not actually be that hard to get this, which is pretty cool. These are done. Let's clean up the previous problem. Euler 11. Did we still have the assembly for strided? No. Okay. So Euler 11 is done. Okay. So there's our U64x3 type. Let's put in the functions for those. So let's see, there's sum. So sum U64x3. We're going to pass an A and a B there. 64x3 mol small U64x3. So mol small has an A of U64x3 and a B of U64 and returns a U64x3. Here's our quotient, here's our remainder. that div small, and then that's, yeah, like that. Okay, so those are our first functions to implement. Let's get to it. Ooh, I'm excited. I'm gonna put on some music, which I haven't done before while I've been programming. I'm just in a music mood this time. Okay, let's grab this real quick. So let's see. I'm just going to turn our notes into some comments real quick. C0, R0 equals A0 plus B0. C1, R1, A1 plus B1, R2, A2 plus B2, C1, R1 equals R1 plus C0, C1 equals C1 or C1, R2 equals R2 plus C1. Okay, so there's the algorithm we want. Let's see if we can type that in properly now. So let's see. First of all, we're going to need, just use RAX here as our accumulator. We're going to read from RA0. So that's RDX, and we're reading a quad word, an 8-byte value. We're reading 8 bytes out of A and putting it into RAX. Then we're going to add into RAX 8 bytes out of B. Now we want to know, we want to set we're going to use R9. How do I want to do this? Is there any way to like read the carry flag? Let me just Google that real quick. Doesn't answer my question at all. I understand it. I'm asking, is there any way to directly read it? Okay, I'm gonna go with no. So that means our options are like conditional moves and conditional jumps. Soon to Moon, what is Project Euler about? Let me go show you Project Euler real quick. Yeah. So Project Euler, this is the like you can just find it if you like search it on your search engine, but it's basically a bunch of math problems that they're aimed at, you know, like the sort of advanced math problems and advanced computing problems at the same time. You have to do a certain amount of mathematical work to understand the problem. They're not just like, hey, you know, implement like a logic puzzle. They're more like combinatorics, primes. In this case, you know, the implementation of arithmetic. And I don't know, you can just look at it. I'll show you their, when you have an account, so I have an account on there, you can look at this like array of all their problems. And we're just solving problems from the first block of 100. And those are the only ones I'm allowed to solve publicly. They ask you not to show the solutions to problems after problem number 100. But you know, you can look at some of these, and let me see if I can find one. There we go. So like, the divisors of 6 are 1, 2, and 3. This is problem number 401. The sum of the squares of these numbers is 1 plus 4 plus 9 plus 36 equals 50. Let sigma 2 represent the sum of the squares of the divisors of n. So if we take that and that and that and that and add them together, we get 50. They're saying make that into a new function, sigma 2, so that sigma 2 6 will be 50, right? Sigma 6 has 1, 2, 3, 6, 1, 2, 3, 6, each of them squared, looks like that. There's that. So then the capital sigma 2 is the sum function of sigma 2. So it's basically what happens if you take sigma 2 1 plus sigma 2 2 plus sigma 2 3 all the way up to n. And then it shows the first 6 values, so like 1, then 5 more, and then 10 more. Eventually we'll find right here it went up by 50. That's when we added in sigma 6. And then it asks you this crazy thing. Find sigma 2 10 to the 15. Right? So like, you could probably imagine writing some simple code that would like be able to handle, like, count the divisors. We'd go up to 100, we'd add them up. How are you gonna do 10 to the 15? You know? Now, for one thing, it's telling you to do it modulo 10 to the 9. So that's, you'll be able to use some math tricks to like say, okay, we're gonna simplify. We're not gonna do that much addition. What we're gonna actually be doing is handling the low digits of the addition. But still, how are we gonna like compute all of that sum? Are there some tricks? Do we really just brute force it, or like you gotta know how much math to use to simplify the computation, and then you have to, at some point, you can't do the math. Like you're not gonna be able to do by hand all the math involved, and then you switch to computation and figuring out. Like, I like these puzzles or these problems because they force you to like engage multiple axes of problem solving skills simultaneously. Okay. Let's see. Okay, right. So this is the one we're on. We were doing sums. Okay. So I determined I'm gonna need to use the carry flags by using Set byte on condition. Okay, this is what I need. So can I give this a 64-bit? I doubt it. Many of the set CC instruction opcodes have alternate Okay, so I think it's just going to set the first byte of the register. I'm not going to be able to make it do less than, or more than that. So it might not clear the rest of zero, but I'll just have to be careful not to use the whole register. So I think I can do set carry R9. I think that'll work. Oh, R9B for byte. So I tell it, hey, just worry about the first byte of R9. Set it based on the value of the carry flag. So now R9 has this, and RAX has this. Okay, so R0 is the final, so I'm just going to write that out. So we're going to say result 0 equals R0. Okay, so RAX is done. Now let's compute this addition. Let's move into RAX. From A is in RDX, plus 8, so we can get the next slot. And then use R8 so we can read from B, plus 8 to the next slot, add that in. And now we have RAX is R1, well, the slash R1, but we need somewhere, so we'll have R10. R10 will grab the carry flag in its byte. And then we want to, let's go ahead and combine those. So R9B, R10B, is that good? Good. Okay, so now R9 contains, the first byte of R9 contains the result of this computation. R9, we no longer have the hat version or the slash version, so we're done with those. R10 is free. RAX is not free yet. What we need to do now is compute R1. Wait, we don't have... Oh, okay. So this is not... Okay, sorry. That's not... Wait, C1 hat. Okay, I jumped the gun. So we have R1 slash. We need to compute so here's C1 slash. So now what I want to do is I want to add now I need this to be cleared to 0. So do I 0 it first and then set it? Or do I have like a truncate operation that would be better? No. Okay. Okay. Just gonna clear R9 to 0 before we set it. Same thing with R10. Wait, it's just confusing because it said it makes it 0 or 1, but it didn't say if it applies to the whole register. Even it says it only. I mean, we can only tell it about the first byte. Points to a byte register or a byte in memory. The condition code is the condition being tested for. Alternative mnemonic sign languages represent the reg field is not used for set 16 times. The code bits are ignored by the processor. Fix at 8 bits. Use of additional byte registers. Otherwise, this instruction set is in legacy mode and compatibility mode. It just doesn't say, so I have to assume that it doesn't, I think. So I'm clearing the whole register to 0, and then I'm setting it. I should probably do the clears to 0 before I do the add so that it doesn't affect the bits of the carry bit. I don't know if it would or not, but just in case. So now we want, let's see. /R1 is living in RAX right now. C0 is living in R9. So we're adding that to that. We're going to need a different one. So RAX now contains the real R1 and the hat version of C1, which is whether or not there was a carry after this add. Now we can send to the destination memory the computed value of R1. Now we have everything we need to compute this. So let's see, R9 was C0, so that one's free now. I'm gonna say, let's make, well, that does not make a lot of sense. Let's just OR together R10 and R11. They both contain one of the C1s. So now R10 contains the combined C1. Then we can add these together. So we're moving into RAX, the 8 bytes that we find at A plus 16, B plus 16 gets added in. then we add in C1, which is an R10. Then we can do result 2 equals R2. Finally, to return, we need to put the return pointer into RAX because the ABI demands it. Okay. So let's test that out. How can we test out if this is working? Well, one idea I have is we could just start by typing in a couple of these things. So like, let's say I want to add that in the first slot, that in the second slot, and that in the third slot, to that in the first slot, that in the second slot, and that in the third slot. Right? This should just look like 3 additions and nothing else weird happening, right? Okay, cool. So now let's try to make it do a carry. So we have max U64, right? Yep. Cool. So you see what happened here? We took 2 things that we're not gonna, when we add these 2 together, max U64 is way, way, way bigger than 10. So when we get very close to max U64, subtracting 10 out and then add, like we're basically saying add those together, it's way past the halfway point, so it's gonna roll over. But then that rollover got seen here. Right, if I put an 8 there, we'd go up to 10, right? So there's adding. So let's do the next one. Mul small. All right, so here we're going to have a result. RCX is going to be our result pointer. RDX is going to be A, also U64 by 3 pointer. R8 is going to be B, a U64. So we want to multiply these. Let's go look at how that computation works. Right, so we need to use the mul here that gives us the overflow. So it's got, we don't want to use imul, we want to use mul so that it's unsigned, and we want it to be mul so that we get the high bits and the low bits. Which means we have to use RAX as one of the multipliers, and then only other multipliers can be arbitrary. So let's do this. Let's first type in the comments. C0R0 equals A0B. C1 R1 equals A1 times B R2 equals A2 times B hat C1 R1 equals bar R1 plus C0 R2 equals bar R2 plus bar C1 plus hat C1. All right, so that's the notes. Let's try to pick an order here. When am I done with R0? I'm done with R0 right away. So we compute R0 and free it up right away. And then if I compute R1, I can combine /R1, I can combine that with C0, and then I can throw them both away. And then I have these and this. I can add that and that together right away, and then I can compute this and add that in. Okay. So we want to use RAX to store whatever's in A slot 0. So that's going to be a keyword putter at RDX. Then we want to multiply by B, that's R8. Now RAX, oh, that's going to, okay, we need to move A to R9. Because RDX is going to get modified by mul. Okay, now we have C0. Cool. So now we want to do. We can output R0 right away. RAX contains R0. Okay, so RAX is free again. Now what do we want to compute? Let's see. We have C0 ready to go. So if we had /R1, C0 would be done. So let's grab /R1. So we put into RAX. Now from the next slot of RDX. Multiplied by B, which is living in R8. Now, okay, we have a problem. So RDX needs to get we need to move C0 to let's see who's free, R10. R9. R10 gets C0, which is an RDX. So we've done A1 times B. We have slash C1 living in RDX and slash R1 living in RAX. Now we said we want to do this add next. So we want to add together R1. R1 is in RAX and C0, that's in R10. So that gives us this add. R1 is here. We'll have R11 ready to catch this carry flag. So R11 is a 1 if that add did a carry. And now we have actual R1, so we can output that. There's actual R1, and now let's see. We can do C1. Yeah, so let's do this. Let's break this up. C1 equals slash C1 plus hat C1, so that we can combine those. So add together, who has slash C1? I think RDX still has that. So let's put R11 in charge and put RDX. We're going to add RDX, which has slash C1, into R11, which has hat C1. Now RDX is free, which we need it to be free in a minute anyway, so we could kill two birds with one stone there, kind of. And now this that we need to do is that. Here we can complete the next multiply we need to do. RAX is free, RDX is free. Yep, we're ready for a multiply. So set RAX to be equal to the third slot. Multiply B. Now RAX equals slash R2. Compute real R2 by adding in C1. C1's in R11. And then we can set result 2 equal to R2. Finally, like before, return the result pointer, because the ABI demands it. Oops. There we go. Okay, so I think we just implemented multiply. Let's check that one out. So let's see. One test is that if I multiply anything by 0, I should get 0. So let's see if that's true. Oh wait, whoops. There's a 0. What if I flip it around? What if the big number is huge and I multiply it by a small 0? That's also 0. Okay, what if they're both the number 1? Okay, what if this was the number 1,000,000? Okay, what if this up here was the number 1,000,000? what if we wanted to overflow the bounds of a U64? So a trillion, so like a million, let's look at it, 1,000 is 10 to the 3, million is 10 to the 6, billion is 10 to the 9, trillion is 10 to the 12. 64 bits, if I plug it in my calculator, 2 to the 64 only goes up to 10 to the 19. 10 to the 19 is as big as it could get in terms of powers of 10. So a trillion times a trillion can't fit in one U64. So I should see an overflow. And hey, we see an overflow. Now, is that a trillion times a trillion? We don't know, because we don't know how to read this as decimal yet. We're reading it as two separate slots of U64s. So it's being multiplied, it's being like rounded or reduced modulo 2 to the 64. So in this slot, so it doesn't look like a trillion times a trillion. But that could be right. Let's see if we can think of a way to test it to make sure that it's right. So what we could do is put in something that is a power of 2, because that should show up as something we recognize. So we can make powers of 2 pretty easily by going like this. So there's a kilobyte, a megabyte, a gigabyte, a terabyte. So 2 of those should be about the same as doing a trillion times a trillion. Like that. So this would need 80 bits to be stored, right? And we can see we get a power of 2 in the second slot. And that power of 2 happens to be 2 to the 16, which is how much over 64 we went, right? We said we needed 80 bits, and we only have 64 bits in the first slot, so we use 16 bits in the second slot. Makes sense? It makes sense. And now, just for fun, let's see multiplying 2 of the max U64s together. Boom. Came out with a 1. I think that makes sense. Here, I'll show you why I think that that's a good verification. So, what we did was we did 2 to the 64 minus 1, right? That's the max U64, times 2 to the 64 minus 1. And we don't know what, like, that's just, I'm not going to write out that for you by hand too much. But instead what I'll do is I'll analyze these symbols a little bit and convince you that a 1 in the first slot makes a lot of sense. So let's see, we get 2 to the 128 when we FOIL that by that. Then we get minus 2 to the 64. And then we get that again. And we get minus 1 times minus 1 is plus 1. So when I FOIL it out, I get this. Now, if you look at it, all of these, I could factor out a 2 to the 64 from. So this is 2 to the 64 minus 1 minus 1. So minus 2 plus 1. So it doesn't matter what this is. This is a multiple of 2 to the 64, right? This whole thing is a multiple of 2 to the 64. So that will not show up. That will not affect the value of the first slot at all, which means that is what we should expect in the first slot, and it's what we see. So cool. I think multiply is working. Next up, we got to do divide. Computation. Ah, yes, I was excited about this one the most. All right, so our parameters are going to be a result RCX, a result pointer, which is a U64X3 div result pointer, our dx is going to be our numerator, and we'll have that as a u64x3 pointer. Our 8 will be den, just a plain old u64. And so now the computation we need to do is this. So let's see, how do we set this up? N2 div d. So N2, first of all, I'm gonna probably need to move our dx, right? So move num into R9. So RDX is free and RAX are free. Now we want to do num2 div den. Just, I don't like that. That was an experiment. I didn't like it. So back to N and D. N2 div 2 D. So I'm going to move into RAX N2. So N2 is living in, this is R9 now, and that's at plus 16. We're going to clear RDX, and then we're going to do div by R8. Now RAX is our Q2, and R2 is in RDX. So we can so result 2 equals Q2. So I want to move into, let's see, our result pointer is still in RCX plus the 16 to get us to the second slot. So Q2 is in RAX. Next, what we want to do, RDX, our remainder, needs to go into RDX, the high bits, but it's already there, so that part's just done. Okay, and then so the remainder of the previous one becomes the high bits of the next one, and then we want to set RAX by reading from here. So there's our high bits, low bits. Then we do div. So then we divide by D. We've got Q1 and R1 now. So we can move Q1 into this slot here. And then again, we can get these from this. This should have been plus 8. We read that. We use the same remainders we had before. So that we do the divide. Now Q0 needs to get written out. This is so cool. The fact that RDX, the remainder, lines up with RDX, the high bits, is the right thing for long division. It suggests to me that that's by design. That's so cool. Right? That's like, I don't know. That's just really good. That's just really good. So let's see. I'll put RAX there. And then finally, we want to output the remainder. The remainder goes at RCX plus 24, and it comes from RDX. And then return the result pointer. All right. So that should give us division. Let's give it a look. Alright, so that should give me a 1 the way it's set up now. Cool, it did. What if I divided by that? I should get a 1 and then a remainder of 1. Cool. What if I divide by 1? I should get a remainder of 0 and a max U64. Cool. If I divide by 2? I mean, yeah, I guess. What if I divide by max U32? Suppose I took 2 to the power of 30 divided by 2 to the power of 15. Cool. Okay, what if I took that divided by 2? If I did that divided by 3, you get a remainder of 1. Ah, this is so cool. All right, I think it's just working. I think it's good. So we've now done all of the arithmetic, but we haven't finished the problem, right? So what's next? Let's see, where did we write down our plan? So we did these, we need to do these, right? The decimal to U64 by 3 and U64 by 3 to decimal. So let's, I don't think we need to sketch those out. These are fairly, well, it might be worth it. Yeah. Let's sketch it out because there is something worth thinking about here. So let's see, where do we want to put those? Put them right here. So let's see if we can read a decimal into a U64 by 3 first. Okay. So The basic algorithm that we could use for something like this is like this. So we have like an input string basically, or stream of numbers, right? So we can call this like, I'll call it n, right? N is like an array of digits. We'll just say int, but it's like small values, or actually not small values, even decimal values. I'll call these base 10 digits. Right, in other words, they're in the range from 0 to 9. And our goal is to turn that into a single x that represents that same number. Now, some other things we're going to point out here. This is big endian. First slot is most significant. So the basic algorithm is to do something like this. You have x equals 0, and then you have a loop, and you go, I guess we'll have like an I equals 0 as well at the beginning. We'll have like x plus equals n, the array, indexed at I. So we grab the next thing, we add that in. Actually, that's a lie too. That's kind of conceptually what you start with, but what you want is that before that, you're doing a times 10 on the x. So x times equals 10, x plus equals n(i). Now, why is it times 10 first? Well, because we're about to put in a new digit, right? This is going to be the least significant digit that we've accumulated. That means all of the digits need to get shifted over first. If we shift over after, then what we're saying is that if we had a single digit, then it always is at least 10, right? If I give you a 1 and nothing else, you would do 1 plus 1 times 10. So the easy way to get it right is to say first shift to make space, then add in the least significant digit that you've seen so far. And then you do I plus equals 1. And then this is like a loop of I over array n, right? So that like goes from 0 to the end of the array n. We could do it like this, loop. Well, I is less than the count of n, whatever, right? Something like that. So that's the basic version. Now here's the thing. If we do it that way, lots of moles by 10, if we do it this way using U64 by 3s the whole time, it's more expensive. So what could we do differently? Well, what I think we should do is break it up a little bit. So what we could do, if we look at like, if we just look at like an example number here, Okay. So we know that we can get 18 digits into a 64-bit integer. So what we could do to unpack something like this is say, okay, start reading and put all of these into a single U64 and then add that. So we first accumulate same thing with this, right? Another U64 here. Then what we do is when we finish a batch, we go, okay, we got to 18, we can't do more than 18. Then what we'll do is we'll take that U64 that we've got and we'll put them together into a U64 by 3. So it's like the same algorithm at 2 levels. First, we run this algorithm here, right? And here separately. And then one more time we treat these as sort of the inputs to the same thing here. So if I have, this number as a 64-bit integer, then I'll put that into U64 by 3. Then when I do this one, I'll go 1, 2, 3, 4, 5, 6, 7. So I've got 7 new digits coming in. So I'll need to do a single multiply with 10 to that power, so 10 to the 7, to shift all the other digits, and then I'll add in the new part. So let's try and write that. See if we can do that. So we want something that gives us a U64 by 3 from a decimal. All right, so that's going to be like a U8. Let's see, we did this last time. What does the Euler data look like? Euler data, U8s and a count. Right, so we pass in digits. They'll already be converted from ASCII to the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then this just has the job of treating that as a task to get converted into a U64 by 3. So then what we want to do is say let's run, set up a test here, N0 or X0. U64 by 4, that's not what we're doing. 64 by 3. So we want to take data.v, I think, 50, right? We know that the problem told us these are 50-digit numbers. So if 2 is the first column, yeah, 52 tells us that there are 50 digits there. And then we want to print that out. Now we just need to implement that, and it will actually work. Supposing we implemented it correctly, I guess. Or, assuming we implemented it correctly, I suppose. So we're going to have a result pointer. has our count, a U64. Okay. So to convert those digits to the thing we want, let's start with just accumulating one U64, right? So we're gonna need a few things. I need a pointer that I can move. I think RDX will work just fine. No, it won't. So I'm gonna need some non-volatile registers this time. Let's start with R12. Move footer equals digits. Okay. We can free up R8. One pass last equals putter plus count. Okay, so R12 is our pointer, R13 is our one pass last spot. And then what we're going to do is we're going to have a loop. Now let's see. I don't know the condition on this loop yet, but I do know some things. So this loop is basically going to look like this. So let's start sketching out the parts we do know. We need an accumulator. We'll call our accumulator X. And we want that to be 0 initially. So we're not going to do any function calls. So this can be, we're not going to do any function calls until we're done with this. So we're going to just put that into, I guess we also want, I'm going to save R15 right away. Or why don't I save like, I'm going to save RBX. And I'm going to move the results pointer to RBX. Because RCX is another one we're going to have to trample over when we're doing function calls. And then when we're done, and we're setting the return value, we'll get that from RBX, and that should be good. Okay, now, X equals 0. Let's make, I don't know. I guess we might as well make RCX ours X. So RCX is X. It starts off at 0. Then we do X times equals 10. So here's where we are still doing a multiply. We're doing a multiply if I made RAX, does that work? No, but you would let me do this. This is why I didn't do it that way before. Anyway. So RAX is now our accumulator. But if I were doing this with U64 by 3s the whole time, it might make the code a little simpler, but we'd be doing a full function call here. And now we're just doing a mul instruction. And then we want to do, after that, X plus equals digit, or star putter, right? So we want to add into X the thing at our pointer. Our pointer is the R12 register. So there's the multiply, there's the add. Then we increment the pointer. All right, so there's the loop. Now, the only thing is we want to stop the loop under a couple of different conditions. If the pointer reaches the one passed last, or if we've accumulated enough digits that we need to stop, right? So we can accumulate a certain number of digits that a U64 won't be able to hold, and then we need to stop. So let's check those conditions here. We know... Okay, we want to check the pointer right away. So if putter is greater than or equal to 1 past last, go to done. So we're going to compare R12 to R13. R12 is our pointer, R13 is our 1 past last. Jump if that's above or equal to done. So here's done. And I suppose something we should probably do right away is like clear result to 0. So if that's above or equal, go to done. Okay, X accumulates. That's good. Okay, so then the other thing we want to check is we want to do this check afterwards because we know after when the loop is just starting that it's not possible. But after the first step, so like here, this check is necessary because we don't know how far the pointer will have gotten previously, right? But then later we need to do this check because we know if we've just come from here that check's not necessary. But down here we've done a mul here, and now like we've done an accumulation, and now it's necessary. And so we have X, which is telling us what actual value we have, but we need like another one. I'll call this one M for multiplier, and it's going to start off at 1. So we're going to move, let's make, let's make RCX our multiplier. So here we're just going to do another times by 10. And the reason for that is we need something that's keeping track of how many digits we've accumulated. So like initially we've accumulated none and we have a 1 there. When we've accumulated 1 digit, we put a 10 there, and so on and so on. So like that could be just an add, but and then the problem is we would have to like do powers of 10. We'd have to do 10 to a power, and so you'd end up with moles by 10 anyways. Although you might be able to, in theory, do less moles. I don't think it'd be faster. I think this is plenty fast. Okay, so we have our multiplier, and now what we want to do is say, okay, we've accumulated this much. If this here's like our go to loop 0. if m is greater than or equal to, and we want the number 10,000 or 10 to the 18. So there's 1, there's 10 to the 3, there's 10 to the 6, here's 10 to the 12, and here's 10 to the 18. Okay. So we're going to compare m, which is an RCX, to this thing. Constant value too large, huh? All right, let me think about how I could deal with that. First of all, let me double check. 1, 2, 3. How big will it allow me to make it? Not very big. So the maximum constant is quite limiting. We would be able to accumulate 1, 2, 3. So it looks like it's probably limited by a 32-bit integer. Okay, so I can do it sounds like I should be able to move a 64-bit immediate into a 64-bit register. Yes. Maybe it's just the parser doesn't like this. Okay. It's not entirely helpful, but it might be a hint. So it says here there's an instruction for 64-bit immediates. But okay, I see. Compare probably can't handle this. Only Mauve could. That's my problem. So let's do this. I think RDX is free. Yeah. There we go. Okay. So I can put a big integer into this register and then use the register, but I can't skip the register because it's a 64-bit integer. That's the issue. And I want to compare with it. So then I can jump if above or equal to loop 1. And everything but loop 1 is good to go. Okay, loop 1 time. So loop 1 isn't really a loop, but it's like the other phase of this loop. So if we get to that condition, then what we want to do is a couple of calls. We want to do a couple of calls and then jump back to loop 0 begin. So here we are accumulating into the final value. And the final value, let's see, that's an RBX now. Okay. So we want to call mul small u64x3 with let's see, our result pointer the result pointer again. Oh, that's an issue. I'll have to double check the code. If they're the same, I may need a separate copy of the U64 by 3 for this to work. I'll have to look at that. Result pointer, the result pointer, and X. No, M, the multiplier. And then I want to call add result pointer X, but I can't really do that. So I do need a separate copy anyways, just so that I can, yeah, I might need to allocate 1 or 2 extra U64x3s in this function. Let's take a look. So let me go look at the code for mul small U64x3. So let's see, when do I modify? It does kind of seem like I only modify it after I read it. So I could be just using the same one in its place, actually, as it turns out. It's kind of nuts. I wonder if the compiler probably doesn't get to assume that when it calls this. That's so interesting. There are so many things that you think you know until you look at this. This is why I'm really happy I tried this project. Same thing here, I read it and then write over it. So I could, in theory, use the same pointer here and here, and it would operate absolutely the way you expect. I bet the compiler just doesn't know, though. Same thing even here. Either of these could be the same as this one, or they could both be the same as this one, and it would still work. Yeah. Okay. Okay, so we're going to call these RBX, RDX, RCX. So only issue is that I've stamped over RCX already, and I wanted to carry it over at least this far. So let's put it in a different register. Let's say it can be volatile, but it needs to be one that, let's see what registers are available. R8 could be our M. And then we don't have to do anything here, right? It's like a no op. So those both get a copy of RBX. R8 already contains our multiplier. We do need to put X somewhere where we can get to it again, because RAX is going to get lost. So let's put that into a non-volatile register, actually. Okay. Now the only other issue we have is I can't actually put, I don't have an add small, right? So I need an extra slot. So I have two options. I could just write an add small. That might be a smart thing to do. Yeah, let's actually do that. All right, so we need to take a quick detour to go write, oh, sum, not add. I guess I would rather call that add. Okay, let's write add small. The reason for this is just so that you have the ability to call the more efficient version when that's all you need, so that you're not like allocating that extra space and setting extra zeros and fiddling things around when it could have just been a register. And it's a pretty easy one. So what we'll do is this is a U64 now. We'll copy paste this. And then we'll just do some equivalence replacements here. So A0 plus, so B0 is B. So we set that. So B1 is always going to be 0, which means this is just R1 equals A1 now. There is, see, the carrier flag will never get set. That won't get set, so we're just reading out of that. And we're adding in C0, and that gives us R1. We don't need the next carrier flag because adding 1 here can't do anything, and then we write that one out. So we read R1 from there, we add in the carry flag, and we set R1. R2 will never get modified because that's going to be that. C1 is always going to be 0. So we're just going to end up moving out of RDX16. And into we just got to do that. We move out of that one and into that one. There's no actual computation. And there we go. That should be it. So now R8 can be R14, the register we had carrying X. All right. So here we shift to the digits. Here we add in the new ones. Then we go back to the beginning. If the pointer gets to the end, okay, this is a little bit wrong. If the pointer gets to the end, we still want to do loop 1 once. Okay, so we increment, we do loop 1, we go back to the beginning. When do we decide to go back to the beginning? We decide to go back to the beginning let me think about it. So what I got wrong here is that if I jump to done, I'm skipping this, which I actually need to do one more time. But if I have this jump to this, then that's going to jump to that, and we'll just get caught in an infinite loop, you see? We'll go loop 0 begin, we're done, final step here. I could have a separate one that doesn't jump back. I could have an if here that says if we're not done, jump back in. But then if there's going to be an if here that says if we're not done, jump back in, it kind of seems like we don't need the if here that says I suppose it would mean this could happen down here, and it would be a jump to loop 1. So loop 0 would always jump to loop 1. We would always assume that you enter loop 0. Yeah, okay, let's do it this way. So we're going to say, if your multiplier gets big enough, you go to loop 1. Or, if you've read the last byte, you go to loop 1. If you've just finished doing that condition, then you go back here and you reset the accumulators. But whenever you begin the loop, the first thing you do is you have an extra test. So here we'll run those things, and now if we jump from here to here, or if we jump from here to here, we have some work to do. Then we'll jump from here to here, and we'll have this test again. Now that might seem redundant, but we only do loop begin once for every major phase. So we'll have to do this test twice to figure out you know, this test is happening twice is the point. But if it gets caught here, then that means we're beginning the phase with nothing left, and then we're really done. But if we get somewhere through the phase and then we run out of bytes to read, then we still have work to do. We have to do this. And then the easy way for this to incorporate the test is for it to just always go back to the next phase. So we always come from this to a new phase, and then that phase always begins with seeing if there's actually any work left to do. That seems good. So there we go. That should be giving us a U64X3 from decimal implementation. It's going to be hard to know for sure if this is right, but there you go. Is it an odd number at least? Should have been even. So let's, here's what we can do. This should give us a 0. And it doesn't. Okay, we need to look into that. Okay, one thing I just noticed, this is wrong. But that wouldn't have had anything to do with the, well, it might have. Yeah, okay, that's still wrong. So let's figure out why. First of all, if I run to there, what does the data look like? The first 50 slots. We should just see 50 zeros. Okay, we do. Now let's see what our multiply is doing, or our decimal decoder is doing. Clearing out 0. If I jump to the right now, I should just see that I got an all zeros result. Okay, so the loop is beginning. X0 multiply by 10, nothing happens. Add in 0, nothing happens. Multiply m by 10. We should now have a 10. We do. We increment our pointer. We do. We set rdx to be this giant thing, 18, 10 to the 18. We compare. And if that was above or equal, it's not, so we keep going. We go. Eventually, we do jump to here with R8, our multiplier, being equal to that giant constant. Okay, so now we're going to call the multiplier. So I want to see right now we have all zeros. I should be multiplying this by m, which is this this thing in R8, which is 10 to the 18. I should still have a 0, right? And I do. And then I'm adding in x. Now what is in x? X is currently stored in the R14 register. That's 0. I should still have a 0. And I do. Okay, so I go back. And then we go again. Let's see, the only time this happens, that's still 0. R14 is still 0. I'm not seeing any sign. Ooh, R14 stopped being 0. Okay, I got it. So when we're reading this right here, we're accidentally reading too many bytes. That should be a byte putter. Which is kind of annoying. So let's see, who's free? Is RAX free at that moment? We want to do 64-bit addition, but we're reading a 1 byte, so we have to split this up. So we read and 0 extend, and then do, so we're reading in the 1 byte range size, but turning it into 64 bits and then doing 64-bit addition. We didn't want to do 8-bit addition, which is the only way you can do it in a single instruction if you're also doing a 1 byte read. Okay, so that gave us zeros. Now what if I parse this? That should give me a 1, right? Okay, if I parse this, I should get a 10. Okay. Somewhere along the way, it will stop fitting in that first slot. And just move a couple zeros over at a time until we see it suddenly pop. Here we go. There it is. Okay, so that looks better to me. Let's look at this one. It should be even. It is. Okay. So I think we're decoding properly now. We haven't like fully deeply verified it, but it looks probably like we are. The best way to verify this is going to be to write the encoder that encodes decimal from a U64 by 3, and see if they together can verify each other, right? Because if I can put in a decimal sequence and then get the same decimal sequence out, that will be a pretty good indication, because the code's complicated enough that it wouldn't really make sense if there were like, it's possible that 2 different bugs will cancel each other out in there, but you know, you'd have to, you're sort of making the odds of bugs work against each other there. If I have some probability of a bug in code A and some probability of a bug in code B, sure, but the probability of them being bugs that cancel each other out is a lot smaller than the probability of there being a bug in each one that will cause garbage, and until I get the garbage cleared out, it'll go away. So I'm going to be basically saying the chance that I have a bug is reduced to the chance that I have 2 bugs that cancel each other out, which is a smaller probability than just the chance that I have a bug, right? That's the kind of the idea of that style of testing. So let's do that. We want to write I'm not sure how many digits this can handle. Let's see. 2 to the 190. Wait, 64 times 3. Yeah. 2 to the 192. 57 digits. So we're going to say that you have to give it a buffer of at least 60 bytes. Right? That's a nice round number that should definitely work. So you put in a buffer of 60 bytes, and we'll return to you how many bytes we actually used. So let's talk about how this one could be implemented. Here we go. So here's how we're going to do a U64 by 3 to decimal encoder. All right, so again, we can look at the basic algorithm. So the basic algorithm for going the other way around, we've got something in code that's it's a compact integer type, and we want to unpack it or encode it into base 10. This one is the one that involves dividing. So we start off with x is our I'll say a U64, or I'll just say int, like I did in the other one. So x is our integer. And we want to do a loop. And what we're going to do is we're going to have like an output buffer. So like putter equals out. Now, what we'll do is we'll say, give me r equals x modulo 10, and then x equals x divided by 10. So we are doing, as we know, this is one instruction, one to get gets us the remainder and the quotient at the same time. But to write it as like C style, we write it as two separate expressions that look like two different computations have to happen. And then what we do is we take this part here, the remainder, and that's the least significant digit that x has, right? So what we're going to do is we're going to write that out to putter. And we're going to go to the next value the putter can be at. So we're going to move the putter up. And then we keep that loop going for as long as x is greater than 0. Now here's a thought, right? What this means is prints digits in little endian order. The least significant digit comes out first. So after all that, you have to like take a minute to go reverse the range from out to putter, right? You just swap all the digits once, and then you're done. So that's the basic algorithm, and that's what we could do. But that would involve again a divide at every step. So I don't know if I can do this one, but I want to think about if there's a way to do less divides. And the way I think we could do it is basically we would do this, but we wouldn't use 10. We'd use something much bigger, like 10 to the 18, right? We could take our big num and we could take x and treat it as our big num, and we would do some large 10 to the 18 style division here. And that would give us a remainder and an x. The remainder would be in base 64, or would be in a U64, and we could then run this algorithm again. So it would be like before, except that the hierarchy would be inverted, right? So instead what we could do use a much bigger power of 10 divider, like 10 to the 18. And then what we're doing is we're saying take the big number, do the big number work, and then unpack the rest of the decimal representation from r directly, right? So we get back r, x will still be a big num, but r will be the remainder, and then we go into a subloop. And then we unpack that U64 using the original algorithm, and we use a single pointer walk for the whole thing, right? So there's the idea. Let's give that a shot. Now, first of all, you'll notice I put asm on this one, and that's because we're going to do a little bit of C++ side work with this one. So we said we need 60 bytes. So let's see, we're gonna grab a count from here's our buffer, here's our X. We get back a count, and then we'll pop that back. So the memory we didn't use, so here's the memory we asked for. Here's the amount we actually used. We put the rest back. Yes, after I should do an align. Right, how do I, there we go. I should just always do an align after these, now that I think about it. If they're not multiples of 8 when I do them. Okay. Okay. And I kind of want to do a special case here in C just because it's too annoying to handle it in it's too annoying to handle it in the assembly. Because you have to do this test for 0. And then put a constant pointer in there and stuff. It's just totally different. So 0 is weird because you would technically get a length 0 if you ran the algorithm. You would get a length 0 and like an empty array. But we kind of want we kind of want it to actually like be non-empty and say that there's a 0 there for printing purposes. So I don't know, maybe we don't want that, maybe we do. I don't want to have to, since I might change my mind about that several times, I don't want to put it into the assembly and have to reconfigure the assembly a lot. So I'm going to do that part in C++. But for everything else, we know we have a non-zero number, which means that we will use at least 1 byte of the array for something other than a 0. The buffer cap count. Okay, so that should do it, except we have to write the assembly. I gotta tell you which arena to pop. Okay. Proc. Alright, so RCX is going to be our buffer, a U8 pointer. RDX is going to be our X. Yes, a U64 by 3 pointer. All right. So what was the plan? First, we want to do this idea using the big numbers themselves. So let's see, we have an X. We need to set a pointer. So we're going to be doing function calls. So this is where we're going to do some setup of non-volatile registers. So let's move buffer into R12. Putter equals buffer. R13 from R12. Okay. What else are we going to need? I just realized I still have to do a 0 test, which is gonna suck. But anyway, we need a loop. This time, our loop is immediately going to do a call to div small. So div small U64x3. So let's see, that's going to need... We need a slot for the div result, so we're going to need to allocate that. We're going to need to pass it x. X is living in RDX right now. It needs to live somewhere else, so I'm going to have it live in R14. And then it needs D. So that needs to be our 6, 12, 18, right? All right, so RCX gets something we don't have yet. RDX gets R14. R8 gets this guy. And then we do the call. Okay. We need to subtract the RSP by, let's see, 8 times 4, so 32. That gives us that the stack pointer is now at the beginning of the stack pointer points right to our div result slot. Let me think. We can't actually modify x in place this time. So what I'm going to do is I'm going to have the div slot, yeah. There we go. You just gotta do 6 moves there and move stuff around. Let's see, what else we got going on? So then I tell you here's x. You give me back the division with the new value of x, and the remainder is at RSP plus 24. Okay. So let's see, we want to put, so I need like a different name. I'll call it U. So U is going to equal div result dot r, and we will put, let's see, I think RCX is good to go because we're not going to do another function call. So RCX is going to get RSP plus 24. And then we want to unpack that into our buffer. Hold on a minute. I think I just noticed a problem. Yeah, this isn't going to work. So what's going to go wrong is when we do this thing here, what if we get something really small? Like, what if we get a remainder of 0, but that's just because we happen to be looking at a number that was a multiple of this. Like, suppose we're looking at 5 times 10 to the 18. So we pull out a 0. Well, with a 0, we would end up outputting, when our x is 0, we should output 18 zeros, right? But how do we tell the difference between the situation where our x is 0 because we need to output 18 zeros, and the situation where our x is 0 because we need to output no zeros at all because we're done, or the situation where we've already read 20 of the 30 decimal values that are relevant? I just don't think it works. I think we have to do it. Yeah, I think we have to do this. Okay. I think we just have to do this. I can't think of any way to do this without looking at it 1 digit at a time. Yeah. Okay. So so there we go. R equals that. D equals that, right? And then we say star putter equals D. So putter is living in R13. So we take that byte and put it there. That should always be less than 10. So we put that there. let me write down why this doesn't work. Alright, so we'll focus on the basic algorithm. Here we go. So we need to figure out, the only thing we're missing right now is how to test if x equals 0. So how would we do this? I mean, I could just do the opposite check. I could check if the opposite is true. And go into the loop, like go to like a jump to continue the loop if any of the slots is not 0. But I wish I knew a way to like easily do an AND type expression. So let's see what we can do. So we're going to use RAX to grab RSP, test RAX against itself, Okay, I think I get it. So if this is not 0, we're going to jump to loop 0. Right, so we're going to jump into the loop if that's not 0. And then if we keep going, we test the next slot. If that's not 0, we go into the loop. Finally, if that's not 0, we go into the loop. But what we're actually going to do is say if this one is 0, then we go to reverse. This is like done, check. So this is just like implementing short circuiting manually. Test this one. If it's 0, or if it's not 0, then we're done. If this is not 0, then we're done. If this one is 0, then the whole condition has been satisfied. Go to reverse. That's how I'll implement it. Okay. Okay, so let's implement the reverse part real quick. So how do you do a reverse? So we have the buffer in R12 and the pointer in R13. So what we're going to do is we're going to call this reverse loop. Because you use a loop to do the reverse. And we do a test. So we go, so spot where we're done. And if putter A is greater than or equal to putter B, we're going to repurpose these registers. They're now the ideas of putter A and putter B. If putter A is greater than or equal to putter B, then we go to done. So putter 12 or R12 has been sitting there at the beginning of the buffer this whole time, and the pointer has been advancing. Right? We've been. Oh, we forgot to do that part. Okay. So putter B starts off as R13. It starts off above putter A, which starts off at the beginning of the buffer. Okay. So now what we want to do is swap the bytes. So we can use RAX. We don't actually need to though, we can use AL. Grab a byte putter from putter A. use CL as well for this one. And then CL goes into this one, and AL goes into this one. So we do 2 reads and we do 2 writes to swap them. And then putter A goes up by 1, whereas putter B goes down by 1. And then finally, we go to the reverse loop and keep going. So that should give us a reverse. Maybe we're done. Let's test it. So in order to test it, what we'll do is we'll build x0, and then we will grab an array of U8s, x0 deck, deck from 64, here's the arena, there's the number, and then we're going to print out I guess we'll just do it this way. We'll do a loop. Print data vi. So there we go, we'll get one line. That first line will be the original text, and another line, that second line will be what we got back from x0 deck. And we'll use the count here since we don't know that we'll actually have the right thing. Have you seen FRC Robotics? No, I haven't. What's that? So our thing is wrong, but it is not far off either. Right, it's got the right digits. There's a 0 here that's wrong, and it's missing a bunch. But let's dig in and figure out why it's only got a few of the high bits and not. Oh, you know what? We never set RAX. Yeah. Okay. So before we do all of the rest of this, AL, let's use DL instead. Reverse loop. No. That's not it either. And it's really big. You won't probably be able to send a link, but you can whisper it to me. Are we still... Something's still... Close this. You can calm down. There we go. All right, let's see. Why is R13 minus R12 wrong here? Nothing I did should have affected RAX. I don't understand. Let's step through it. So here's deck from U64X. R13 is equal to R12 when we're incrementing it. What did we just put in there? A 0. Wait, really? I don't think the first one should be a 0. No, yeah, the first one is a 0. That's right. This is reverse order. Yep. We are taking this number. So the first thing we should see is a 0. Can we see what's at RSP? That's our big integer here. So we're about to divide it by 10. Boom. So that's divided by 10. And then we get a remainder. Why don't we make this 4 so we can see our remainder slot as well. So we have a remainder of 5. Good. Can we see the result right after the call every time? Remainder of 2. 0, 5, 2. So those look good. Eventually, we should reach this one. Yep. So x is 0. The last remainder we had was 3. That's correct. So now if I look at R12 as a pointer, and 50 slots, 052, 0475, 052, 0475. You go all the way up to 371, 0728. 75339. Yeah, okay, so these look very much correct. So RAX becomes that pointer minus that pointer. Oh. Sub RAX, okay. Okay, it's almost correct. The only issue is that when it does the swap, for some reason the 0 here doesn't get moved. I think I know why. So before we begin, we need to subtract 1 from this, because this here, the putter B, is 1 past the end. right? Hopefully that makes sense? Like, if I have 10, if I did b minus a earlier, b is the high one, a is the low one, and I got 10, then b is not actually pointing at the last thing. Oh, sorry, not put or b, R13. There we go. Okay, let's try a few more. So we can get the second one. Yep. So that first line is the original data, and the second line is what it looks like after we've encoded it into one of our numbers and then decoded it back into decimal. So I think we're good. Now we can write up a solution to the problem. So let's use these cool tools we've got. We want to do okay, first of all, here's our x. That's going to initially be a 0. And we're going to do a for loop that visits each line of the Euler data. And then what we're going to do is grab like a C out of one of these lines here. So we grab U64 by 3 from a decimal. We use our Euler data plus 50 times our I. So 50 is the number of digits that they told us in each number. I is which line we're on. Our parser has already taken care of removing white space and converting these into the numbers instead of the ASCII characters 0 through 9. So we just need to tell this that this is a length of 50. And then we want to add these together. So x equals x plus c. Then we want to turn x into decimal. So dec from U64 like this. And finally we can print the whole thing. That's 56 digits. It's a little more than I expected, but maybe it's right. So let's grab just the first 10. Fingers crossed here. Oh man. Okay. So in order to check this, we're going to need some way to like visually inspect steps along the way. So let's try, first of all, let's switch back to looking at the whole thing. And let's try just looking at the sum of the first two. Yeah, that seems just too big, right? Like, it doesn't seem like it should be possible for 54 digits to come out when we add this plus this. So let's grab there we go. Those and this. So like that makes sense. Let's see if this all like makes sense. 8, 5 plus 3 is 8. 2 plus 5 is not 9. So that right there seems weird. Okay, let's double check each step of the way. So we're going to grab x. And y. And double check that I'm remembering that correctly. Digits count. Realize there's an X in the name, so I can't use the macro, the replace check quite as freely. Let's then print. We're going to print each of those. Here, I can use it. Yeah, it's not variable, it's the same thing every time, but somehow that is different than what we're getting the other way. Right, if I look at that and that, that's not the same thing, right? That right there, it's not the same thing. Let me do this. These don't even match. It's weird, right? But separately, this doesn't look like the correct sum for this. 8, 8. That should be a 7, then it's a 3. How will we figure this out? So let's and let me throw in one other thing. I could also print out the correct version of the values before the sum, just make sure we're not getting an actual mistake there as well. Now those look fine. So the converters are fine. Is it add then? Is add the issue? Kind of seems like add must be the issue. So let's see if we can work out how that's possible. What we're gonna do is I'm gonna convert this into all zeros. Start from there. So there we go, all zeros. Now I put a 1 in each of these spots. What happens? Immediate garbage. That should just be a 2, right? So I'm gonna see if there's like a spot where an issue shows up. So there it's correct. So it's looking like small numbers work, and then probably as soon as it requires 2 slots, there's a bug. We gotta figure out when that first happens. There we go. All right, so there's a bug. Somewhere between there and there, it didn't do the right thing. So let's let's do the thing where we look. So we're gonna look into this with the debugger. Why did it not add those correctly? Okay. I'm not interested in add small. I assume that's because you're doing a it doesn't know how to unwind after this function. I see. Makes sense. Yeah, it's something we could do on as a bonus thing is go and add in the unwind info. Okay, here's the add. So yeah, it's this one right here. We should have RCX, RDX, and R8 are all different pointers, so there's no like weird accidentally using the same memory twice kinds of aspects to this bug, I don't think. So let's see. RAX gets that sum, and the carry flag is 0. So R9 should just be a plain old 0. Yes. We write that result. Let me turn these into memory views. So there's our output slot, and these are our input slots. I had an idea of how I could test this pretty interesting. I might explore that in a minute, but let's keep going with this path right now. So let's see. We set the output to be the sum of this and this. That looks like that, and there was no carry from it. Okay. Why is that XOR? Yeah, that should be R10. There we go. So yeah, when I was trying to clear R, so that confirms a few things. One, this does not clear it to 0, right? This does not clear it to 0 at all. So when I was trying to clear R10 to 0 before I did this, I was accidentally doing it wrong, and I was XORing R10 with 10 instead of with itself to make it 0. Whoops. So then if I do this, that sum looks right. 8, 8, 7, 0, 0, 9 plus 1 from the carry there. 5 and 8 is 13 plus 1 from the carry. 3 and 1 is 4 plus 1 from the carry. 1, 7, 2. Yep. Okay, looks good. 1 from the carry here. Good deal. All right. So let's try this again. First of all, when I run it this way, I'm getting the right result as well, right? Yes. So now let's run it on all of the lines instead of just the first two. Okay. 53. So that's more like the size we were expecting it to be. Let's grab the first 10 digits. We did it. Oh man, that's so cool. Wow. So yeah, there you go. We've got 192-bit integers that can do addition. They can do multiplication and division with 64-bit integers, but not with other 192-bit integers. And we've got the ability to parse them and print them. It's pretty cool. Pretty cool. Yeah. Okay. I'm going to wrap it up there today. So we just got one done, but it was a big one. It was one we spent a lot of time on. It was definitely a fun one. So let's see. I think next time we'll be digging into this one. It's a very mathy one. Yeah, nice. I'm just vibing to this music for a bit before I wrap it up for the night. Alrighty. Thanks everyone. I will see you guys next week where we will pick it up with the Pythagorean triplet problem. See you later.